In this video, we are going to discuss how to determine the pre-consolidation pressure using Casagrande's graphical procedure, which he developed in 1936. So if you recall, the pre-consolidation pressure is typically called sigma prime sub P, or sometimes we call it sigma prime sub C. But again, this is called the pre-consolidation pressure. Okay, now what is the pre-consolidation pressure? Well, this is the maximum pressure or overburden stress or pressure that the soil sample has experienced in the past. Okay, so what we can do is we can obtain this or determine this. So we're going to say this can be determined from any of the four plots that we've previously talked about, but it is most often determined from void ratio versus effective stress on a log scale. So this is what you're familiar with, okay? Now this procedure, we did go over this procedure briefly in CE 322, and you may have even had a light homework on it, but again, we're gonna kind of revisit it in a little bit more detail in this class, okay? So let's look at this general procedure. Okay, so step one, and by the way, this is going to be with reference to E log effective stress on a log scale, E versus effective stress on a log scale. So in our procedure, let's say step one, what we want to do is establish a point A where E versus effective stress, which again, effective stress is on a log scale, has a minimum radius of curvature. Okay, now remember, minimum radius of curvature really means maximum curvature, which means what? It's the most curvy. Okay, so that's step one. Step two is draw a horizontal line AB. And then step three is going to be draw a line AC that is tangent to point A. And then step four, we're going to bisect angle BAC, and let's call it line AD, okay? And then what we're going to do, last step, step five, project a straight line portion of the tail of the curve to intersect AD. And then what we're going to do is call this point F. And then the abscissa of point F is sigma prime C, which is the preconsolidation pressure. Now remember, abscissa means horizontal value, okay? So let's go ahead and just graphically show this out. Let's say we have E, and we have effective stress here on a log scale. And then we know, let's say the data shape looks kind of like this. Okay, this is a familiar shape to you, okay? And so what we do is we, let me draw this a little bit better. Not my best artwork. Actually, that's worse. Bear with me. Okay, that's okay, I guess. So on the loading curve, you're gonna, step one, identify a point A, where we have a minimum radius of curvature, so it's most curvy. Now it's going to be somewhere in this general area right here is going to be point A, okay? Again, minimum radius of curvature, so it may be hard to spot, but it's going to be somewhere in this upper region, and it's going to be where the curve is most curvy, okay? And then we're going to draw a horizontal line, call it AB, okay? So I'm going to project a line from A that's horizontal, and I'm just going to give the other end of that line a letter name, call it B. So that's line AB. And then step two says draw that is step two. Step three says draw a line AC that is tangent to point A. So let's change colors. Actually, you know what? Let's not. Let's keep it red for now. We're going to draw this tangent line at point A. Trying to make it a little better. And give this one a name, AC. And again, it's tangent at point A. Point A is the tangent point for line AC. So that's step three. Now, step four says bisect this angle. So we've generated an angle here, BAC, okay? We're going to bisect this angle, which basically means cut it down the middle, and we're going to call that line AD, okay? So I'm going to change colors on this one. I'm going to try to cut this right down the middle. Did a bad job that time. Okay, and this is going to be line AD here, okay? So that's step four. And then step five says project a straight line portion of the tail of the loading curve. So that's going to be the tail of the loading curve. Do not mess with the unloading curve. We're dealing specifically with the loading curve here. Project a straight line portion of the tail of the loading curve to intersect AD. So I'm going to maybe use green here. So project a straight line portion from the loading curve to intersect AD. I'm going to call that point F, okay? And then the abscissa of F is sigma prime C. So I'm going to come down here. And then this point right here is our pre-consolidation pressure that we're looking for, okay? Now, this curve I just sketched here, you know, this is a very steep tail right here. So it looks like, you know, this is pretty vertical, but it's not always going to be vertical. Let me see if I can maybe sketch this out just a little bit better. We're coming straight down. Yep, here we go. Sigma prime C, okay? And again, it's vertically down. We're projecting it straight down, okay? So again, you know, if let's say we had a different shape of data. Let's say here's E, here's sigma prime on a log scale. You know, you could have data that's very shallow like this, okay? And then maybe you just have some unloading data like this. I mean, you know, the data shape is going to be something like this, but it's not necessarily going to be as steep as the one I just drew. So maximum curvature would be about right here, and you know, here's line AB, and then we draw a tangent line here. That's line AC, and then we have a not a perpendicular bisector, a regular bisector, AD, and then here we project the straight line portion of the tail of the loading curve back up, and where it intersects that bisector, that's F, and so you go straight down, and here's sigma prime C. So, you know, the shape of your data is really gonna determine how you project these lines, but nevertheless, you follow these 5 steps every single time. So here, this point right here is sigma prime C. Okay, and that concludes this video.